Hey everybody, welcome to my term project for digital terrain analysis. I'm going to be going over mapping offset channels using LiDAR for the Hunter Mountain Fault Zone in northern Panamint Valley. My purpose for this project is to show how point cloud data can be used to analyze the geomorphic evolution of this super chaotic tectonic setting through measuring the amount of lateral displacement identified along a small segment of the Hunter Mountain Fault. And I'll be touching on a couple of other digital terrain methods that were introduced during this term. I'm going to briefly go over the setting, talk a little bit about the LiDAR data used, describe my methods for analysis, and then show my results and how to make this a more complete study. The tectonic evolution of this setting is contributed to its location within the Eastern California Shear Zone, a north-south oriented 100-kilometer wide belt of extension and right lateral shearing that accommodates about 25% of the relative plate motion between North American and Pacific plates. Panamint Valley is thought to have developed since 15 million years ago along a low-angle detachment fault system that links extension with the Death Valley fault system, illustrated by the diagram in the bottom left. And then you can see the study area that I'll be investigating, marked by the red star. I'm going to be comparing the amount of displacement for channels through the study area to a previous slip rate estimated from the Hunter Mountain batholith a few kilometers to the north. So there are quite a few geomorphic features commonly associated with strike-slip faults. The diagram at the bottom right shows several of these, such as linear troughs, back-facing scarps, abandoned stream channels, and inset channels that are laterally displaced. The two images show examples of some of these features at different magnitudes. The one on the bottom left is a portion of the study area showing multiple seismic events, where the upper right is probably from one seismic event. The LiDAR point cloud was downloaded from Open Topography for an area just under a square kilometer. The mission was completed by the National Center for Airborne Laser Mapping for EarthScope's Plate Boundary Observatory, which was a program of the National Science Foundation between 2003 and 2018. This particular path of the mission took place on April 18th in 2007 with the Optech Gemini ALTM mounted on a Cessna Skymaster. And I thought it was interesting how much information you could find out about these missions. So I thought I'd mention a couple of things like the scan frequency of 50 hertz, a scan angle of 11.3 degrees, and the average point density of 4.61 points per meter squared. I started by following the LAS processing steps from one of the labs or ESRI tutorials that we completed during this term and filtered to ground points. Next, I generated a half-meter resolution digital elevation model using those last return ground points. Multiple terrain models were derived from this DEM to aid in identifying and placing fault traces, including a hillshade, a slope aspect, shaded relief map, and a 1-meter contour map. I used the linear, back-facing scarps and offset channel inflection points to trace the fault surface expression. I found the aspect slope map overlaying the hillshade to be the most useful for positioning the fault. Bringing these layers into a 3D local scene in ArcGIS Pro shows just how useful creating a 3D terrain model is for fault mapping compared to using topo maps, aerial images, and driving around a desert at specific lighting times. I figured I'd give a shot at the watershed delineation workflow in ArcGIS Pro to mark piercing points for the offset channels using stream thalwags. Following the workflow, these channel thalwags were extracted from the stream orders raster shown here. So 5 offset channels were mapped and measured in ArcGIS Pro, resulting in an average right lateral displacement of 69.17 meters for the 1 kilometer long fault trace. And like I said, the slope aspect map was probably the most useful for identifying geomorphic features compared to, say, the relief or contour maps. And then the 3D scene was super effective for sort of simulating being in the field and being able to walk around these fans and the different drainages. The watershed delineation process allowed for easy identification of channel centers and helped to pick out the abandoned streams that natural color imagery hides quite a bit. And you can see that by the red circles I've highlighted on the hillshade image versus the natural color image. So without an actual age estimate for the landforms being cut and displaced, a meaningful slip rate can't really be calculated. However, if that 2 to 3.2 millimeter slip rate per year from the previous studies is consistent with this area, then the 69-meter lateral offset would put a rough age of 25 to 34,000 years for the pre-faulted fan surface, or the age of incision for those channels, which is pretty young for a lot of these surfaces out there. So the methods for this type of study have been greatly scaled back and generalized to provide more of an overview for fault analysis from this remotely sensed LiDAR data. And a complete tectonic evolution and slip rate study would include fan surface age constraints, statistical analysis of the stream channel thaw wags, and just overall produce a better accuracy for the placement. And just to wrap this back around, the reason or purpose that geologists and geomorphologists run around the desert chasing millimeters in the dirt is to contribute to time predictable models and recurrence intervals for earthquake and seismic hazards. And that's it. Thanks for listening.